Hello, in this video we're going to look at the Nobel Prize in Chemistry for the year 1912. We're going to look at the Nobel Prize lectures given by Paul Sabatier and Victor Grignard. Paul Sabatier got the prize for his method in hydrogenating organic compounds in the presence of finely disintegrated metals, and Victor Grignard for the discovery of the Grignard reagent. First we have Paul Sabatier's Nobel Prize lecture, The Method of Direct Hydrogenation by Catalysis. Here you see the main reaction. This is carbon dioxide with hydrogen giving methane and water. You need a catalyst and 400 degrees Celsius and a lot of pressure. This is an alternative for the same reaction. As you can see, there are slight differences. You have carbon monoxide and 3 instead of 4 hydrogen molecules, and you get 1 methane molecule and 1 water molecule. In the original it was 2. Okay, here we go. The general method, this is summarized by me, by the way. The general method for direct hydrogenation by catalysis I established, is of course Paul Sabatier and not me, with Senderens and later with Melre and Murat. With this method, a wide variety of processes can be done. Here we deal with how I found these new methods, its principal application is mechanisms. 1. Early methods of hydrogenation were almost always based on nascent hydrogen, now iterated concept of hydrogen in a special date. When used alone, in the absence of the reducible substance, it releases hydrogen and heat energy. Transferable systems will add the hydrogen. This is used to make alcohols from aldehydes or acetones, esters or fatty oils, or aniline from heterobenzene, or organic substance for hydroacid, etc. The medium in which the reaction takes place can be alkaline or acid. Sometimes this is dangerous. For instance, the use of hydroic acid, the hydrogen liberates, can have a pressure about 100 atmospheres, so it's quite explosive. The hydroic acid can isomerize to reducible matter, and which is an unwanted effect. The direct use of gaseous hydrogen in the hydrogenating process, first done by Kuhlmann in 1838, Kuhlmann in 1852, Deepers 1873 in the wild 1874, used platinum sponge or black as a catalyst for new hydrogenation reactions. This was the state of the field when I entered it about 15 years ago. This is about 1897. Montlanger and Quink had just isolated nickel carbonyl with carbonate monoxide and powdered nickel. It occurred to me one night add other complete gaseous molecules to gases. Moissan had just made pure acetylene, an incomplete molecule. He thought he might be able to add it to metals. Here Moreau got something different. Acetylene brought into contact with metal immediately decomposes with intense incandescence, decomposition of such carbon and the gaseous and liquid products. He explained this by acetylene entered to the pores of the metal, raising the temperature, then decomposing acetylene into hydrogen and carbon, and the rest into benzene and other hydrocarbons. In reality, the gas was not hydrogen, but amongst others, ethane. Liquids are not simple polymerization projects. I took over the development of this experiment. My ideas of catalytic phenomena were commonly held and influenced by teacher Buffalo. The catalytic activity of platinum is not by physical condensation, but by a chemical combination on the surface of the metal with the surrounding gas. The decomposition of acetylene is then caused by an affinity of metal for acetylene and for carbon/hydrogen. I and Senderens in 1897 made a similar test on ethylene directed to nickel, cobalt or iron at 300 degrees Celsius, and it gives the same results as above: incandescence, carbon and ethane. The ethane had to be hydrogenated, decomposed ethylene, hydrogenation induced by the metal. The nickel is not modified, so it acts as a catalyst. In 1889, we established that reduced nickel has the same catalytic activity. In 1900, the same for reduced cable, iron, copper, powdered platinum, though all less vigorous. In 1900, we had success. Sanders and I found that benzene can change into cyclohexane, hydrogenized, when in contact with nickel at 100 degrees Celsius. We then dared to state that an unsaturated ethylenic or acetylenic hydrocarbons can be so transformed to saturated hydrocarbons and into nitroderivatives into anti-amines. All this without undesired byproducts or isomerization. During 1901 and 1905, Sanders and I showed that nickel is suited for hydrogenation of nitriles into amide and aldehydes and acetones into alcohols. Methane can be made from carbon monoxide and carbon dioxide. Aromatic hydrogenation takes 6 hydrogen atoms to produce the corresponding cyclic compounds with nickel. Tetravalent terpenes can take 4 atoms, divalent terpenes take 2, as predicted by Wallach. From 1904 to 1911, with Mallet, I developed a method, applying it to hydrogenation of the aromatic hydrogen derivatives to hydrocarbons, etc. Hydrogenation of aromatic nucleus in the diphenols, pyrrolgalol and benzamine in the end succeeded, giving cyclohexane compounds. With Murat, I was able, after early failures, to hydrogenate benzoic acid and its ester to hexohydrobenzoic esters. The same for the hydrogenation of diphenyl to diclohexyl. Others also contributed using the same method, like Terzen, Brunel, Guido, Leroux, Brito, Willestetter, Padova, Gideon, Murat. 2 conditions are essential for success: pure substance and a suitable temperature. Powdered nickel as catalyst works like a ferment. The presence of a certain substances are sufficient to attenuate and suppress their activity. Sulfur, bromide, or iodine poison the working of the metal ferment, and this must not be present in the metal. The hydrogen or the substance to be hydrogenized. The temperature must also be carefully regulated. Hydrogenation only takes place in a defined temperature range. Some hydrogenation processes are easily disturbed, while others are not. Now some interesting results, chosen from the numerous. 1. Direct hydrogenation of acetane with nickel. In the cold, acetylene and hydrogen change into ethane. Above 200 degrees Celsius, the yield is methane, methylene, methyl groups, which unite again in various ways. Acetylene alone brought into contact with nickel gives incandescence, breaking down into carbon and to hydrogen and changing the rest into atomic hydrocarbons, benzene and its homologues with additional carbons. The last can with nickel be reduced by the hydrogen into cyclic hydrocarbons and after condensation give Baku-like petroleum. The same procedure with acetylene and some hydrogens gives an intermediate product of straight chain and cycle hydrocarbons, like Romanian-like petroleum. Raising the temperature to 300 Celsius retains a portion of the aromatic hydrocarbons, giving Galician-like petroleum. I deduced from all this a general theory on the production of mineral oil on the earth, building on Mendeleev and Bevelot. And 2. By direct hydrogenation of vapor or liquid fatty acids into solid acids can be used to change oil and hydrogen into solid fats. Then for the continuous transformation of nitrobenzene into aniline, copper works better than nickel. That's probably as a catalyst. Direct hydrogenation of ordinary acetone produces isopropyl alcohol in a cheap way. Hydrogenation action by nickel on carbon monoxide can result in methane. Using water gas without carbon dioxide eliminates the toxic product carbon monoxide. Aromatic nuclei can be hydrogenized with 6, giving a cyclohexane compounds in an easy way. Direct hydrogenation of phenol and paracresol gives cyclohexanol and paramethylcyclohexanol, useful in synthesization of rubber. How to explain hydrogenation by catalysis? The hydrogen acts on the metal surface. It seems that there are several stages of combinations with, for instance, nickel. If this is correct, it can be deduced that the active metal can fix free hydrogen but can only take hydrogen from substrate and give it up. There's also hydrogenation catalyst. At 250 to 300 degrees Celsius, powdered copper dehydrogenates primary alcohols into aldehydes or secondary alcohols into acetones. EPTF found that alumina splits alcohol into ethylenic carbon compounds and water by catalysis. I found also blue tungsten oxide and thorium oxide can do this, though in the end must be oxidized to restore its catalytic power. I again turn to the idea that the temporary formation of the compound for explanation. Thorium play the same role in the production of alcohol as sulfuric acids in the production of ethyl ether or ethylene. An alcohol thoriumate and ester compatible to the acid alcohol sulfide is produced. The surface of the oxide acts like a catalyst and like a sulfate reacts with various substances to form alcohol. If this is true, alcohol vapors can be used to create triols, primarily as secondary amines, oxides, and esters of acids. I can see no other explanation as a temporary compound formed by the catalyst with a gaseous element. One substance can with hydrogen give certain substances with one catalyst and others with another catalyst. This may be connected whether or not the catalyst is metallic, whether or not electrometal contact forces intervene. The results can only be explained by the intervention of special chemical effluent operating at the surface of the catalyst. Well, this is a summary, of course. Not all the arguments are given, which may sometimes make you feel like there's some jumping in, and there are unfortunately a lot of typos in it. I think I used an old version of the PowerPoint to create this movie, which was not spell checked. I'm sorry for that. And here you see an illustration of the hydrogenation of a double CC bound, two carbon atoms in 3 steps. If you want to study it, you better probably pause the video and look at the pictures one by one. Then we go to Victor Grignard, Nobel Prize lecture, the use of organomagnesium compounds in preparative organic chemistry. Here you see a variation of the Grignard reagents. Yeah. Also, if you want to study this, better probably pause the video or go to the original. Okay, then is Nobel Prize lecture. I, as of course, Grignard, do not only speak of my research into organic magnesium compounds, but also of parallel and independent work of others. Like Sabatier in his lecture showed that certain metals can serve as a carrier for hydrogen in order to transform it into an organic compound. Metals can also serve as carriers for a complete organic radical and enable it to be transferred. There are organometallic compounds. Some of them, those of alkali methods, are very active and very unstable and not suited for practical application. Others, as those of mercury, are too stable and hardly react. Last century, only organic zinc compounds were usable. They were discovered by Franklin in 1849, but using them remained difficult. They were unstable, etc. The one metal that could replace zinc was magnesium, which has a lower atomic weight and greater reactivity, but it could not be studied until it could be prepared in a suitable pure state. Leur, Fleck and Waga showed in 1891 to 94 that symmetrical organic magnesium compounds were not liquid. Those of zinc were, but solid and almost insoluble, highly inflammable, etc. Barbier then in 1898 brought the reactant immediately together, causing the reaction between a ketone and a methyl iodide. This was possible with magnesium but not with zinc. I took this up but returned to organic magnesium compounds prepared in advance, not with the Leur method but by the Franklin-Winkling method. Her attempt with zinc did not have a practical value, therefore I tried magnesium. It worked, and gave St. a new series of organic metallic compounds. I will try to describe them here. Preparing organic magnesium is easy, but no moisture or oxygen must be present. Magnesium is brought together with methyl oxide and dissolved in anhydrous ether. An intense reaction is resolved, tempered by adding more anhydrous ether. All magnesium disappears and we get a colorless fluid. The compound presents in all characteristics of an organic metal compound. In contrast over organic zinc compound, it does not ignite in air, but it's still volatile. But we can use it without danger, just as ether. The zinc compounds were all symmetrical, but the organic magnesium compounds are not. In the zinc compounds, one of the two radicals is lost to the reaction. This is not so with magnesium. The magnesium reagents received by me with the formula R magnesium X with R organic radical and X halogen mixed organium compounds. What choice is there for iron X? The choice for X for magnesium is much larger than for zinc. For zinc, some alkaloids, for magnesium bromides, iodide, and chlorides. For R, the limit is the number of monohalides. Another functional group is the molecule in the molecule doesn't prevent reaction, ether, alcohols, and phenols. The double bond may also be present unless it is close to the halogen. Grignard gives several examples, including structural formulae, which I have skipped here. But if you want to see them, go to the original lecture. Pointing to his own work and that of Courteau, Odo, Meunier, there are still more reagents. Again, Grignard is pointing at his own work and that of Vignon, Barbier, Blaise, Hemonet, Braus, and Josicic. Many of these are accompanied by unwanted secondary reactions. The most consistent reaction is the one which results from the removal of the halogen from two halide molecules by a magnesium atom, accompanied by the joining of two radicals, same as discovered by Woods. 2Rx plus Mg give magnesium X2 plus RR. Another secondary reaction results from the elimination of a molecule of halogen acid with the production of a double bond. Using chloride instead of bromide or iodide attenuates this. In general, the reaction of organic magnesium compounds are of two kinds: reaction of substitution or of addition. These compounds react with substances containing atoms of reactive hydrogen, whether or not this hydrogen is joined to carbon or nitrogen or oxygen. The organic radical is then released as hydrocarbon. This was investigated by Chugaev and Odo and Zerevitsov. The action of water in particular can be used for preparing hydrocarbons, as was investigated by Tiget and Grignard. The organic halogenated derivatives, investigated by Tiffenot and Hemonet, readily react, accompanied by joining of organic radicals to give hydrocarbons or ethers. The addition is with different elements as oxygen and sulfur, but there are of more importance when the functional groups in which two atoms are united by some multiple bonds, for instance, carbon, oxygen, sulfur, or nitrogen. In all cases, one of the two bonds is broken. I becomes fixed to one Mg to the other part. Magnesium X, to the other part. Sometimes addition and substitution takes place at the same time. The result is an alcohol, primary, secondary, or tertiary, depending on which substances react. Examples are given which are skipped here. So substitutes for cocaine can be made with less toxicity and the same anesthetic properties. The many alcohols produced with above methods can be used for making ethylenic hydrocarbons, all still using organic magnesium compounds. Hydrogen and hydrocarbons also use rubber by polymerization after the magnesium method is used. Interesting hydrocarbons from a theoretical point are these obtained from magnesium compounds of cyclopentadiene, iodine, and fluorine, all colored. The magnesium method can also be used to make alcohols that are difficult to make with other processes. I also established the first method whereby in an aromatic compound, a halogen or another functional group can be introduced at the end of a side chain. Another thing in organic chemistry is the creation of many methods of aldehyde synthesis, many of which are used which used organic magnetic compounds. Grignard gives 5 examples which are skipped here, but points to ketamine, methylazole, Woodrow, Chichi, Babin, Behelans, Somerlet, Bouveau, Monier Williams, and others, which also investigate these compounds. The same is true for the production of ketones, investigated by Blaise, Bayes, Dozens, and Fourier, and for nitriles and for acids, investigated by Grignard. Interesting is that many reactions occur in the same way, using sulfate instead of hydrogen or sulfate instead of carbon. Investigated by Huber, Weikert, Rosenheim, and Singer. But we can go still further by working on molecules of complex function. First, if the molecule has 2 identical functions. Examples: diketones give deuterium glycols except beta-diketones which react only through their analytic hydraulic function, investigated by Fuller and Zielinski. And the quinones, also like diketones, do not react only through one carbon monoxide group, investigated by Bamberger, Blangley, while the pseudoquinones react through their 2 groups, investigated by Haller and Guillaume. Further, there's work on esters by Valeur and Blaise. Second, if a molecule has 2 different functions, Grignard was able to start the 2 reactions successfully, starting with the most negative. Example: ketonic acid leads to acid alcohols, then to tertiary glycols. The ketonic esters reacts in the enol form. With regard to ketonic esters, I must a new group of synthesis, asymmetrical synthesis. Mackenzie did this and got slightly lavatory alcohol acids, which is an asymmetrical result. Finally, the organic magnesium compounds can produce an apparent fixing to an ethylene bond. This happens when the double bond is near a functional group with a multiple bond. Grignard did it first, later also Ehler, Blaise, Bauer, Blaise, Courteau, but Kohler studied systematically. Last is the survey of the important reaction, the substitution reaction produced by the metallic or methyl derivatives, in particular halogen derivatives. A large number of organometalloidal and organic metallic compounds have been prepared in this way. Investigated by Dilthey, Kipping, Gotonsky, Seganov for the methyloid group, and Blaise for the second group. The reaction is R, magnesium sulfide plus zinc chloride plus R, zinc chloride plus magnesium X chloride. The only way to produce organic zinc aromatics. If that was as it is, might magnesium play a role in the natural synthesis of organized matter? Belser has isolated 3.5 magnesium from chlorophyll and assumes that the absorption of carbon dioxide is comparable to the Grignard reaction involving magnesium. He also compared the chlorophyll of leaves with the hemoglobin of animals. Life due to synthesis by means of magnesium and life due to the oxidation by means of iron, which are problems for tomorrow. Well, I said this is summarized. That means that some big steps had sometimes to be taken, which is of course not always making it more easy to understand. So if you want to understand everything, you have to follow this link to the original lecture. And I also apologize, I probably used an old version of the PowerPoint, which is at the basis of this video, which contained a lot of typos, which I thought I had corrected, but probably not saved. I'm sorry for that, but that's the way it is. Here you see some of the solutions that were used by Grignard. This is probably the first. It's probably an 8-step thing. These are steps 3 and 4. If you want to know more about this, you better follow this link. This was it for today. Next time we will go to the year 1913 and deal with the Nobel Prize in Chemistry and also Physics and Medicine Physiology for that year. For now, thank you for watching and maybe till another time.